Hey everyone, today we're going to be learning how to describe the transformations of square root and cube root functions. So in the previous video, we learned how to figure out the domain and the range and how to graph these functions. But now let's learn a little bit more about the transformations of each parent function. So before we start learning the transformations, let's quickly take a look at how to state the domain of each function without graphing. So in the first example, we have f of x is equal to the square root of x minus 12. So we know since we're taking the square root over here, we cannot have a negative value as the radicand. So the number inside of the square root symbol cannot be negative. So we're going to start out by saying, well, x minus 12 has to be greater or equal to 0. And since I have minus 12, I'm going to add 12 to both sides. And then that leaves me with x can be greater or equal to 12. So for my domain, that's all I need to write. X greater or equal to 12. Think about it. If I put 11 here, this would be 11 minus 12, which would give me a negative 1. And we know that the square root of negative 1 is an imaginary number. Okay, now let's move on to the cube root function. F of x is equal to the cube root of x plus 7. Are there any numbers that I cannot have inside of a cube root? There are no restrictions for cube root because I can take the cubic root of a negative number. So for instance, the cube root of negative 1 just means what number times itself 3 times gives me negative 1. So negative 1 times negative 1 would give me positive 1, but then I multiply it by negative 1 and I get negative 1. So for that reason, we have all real numbers when we're dealing with the cube root. And that is going to be the case whenever you're dealing with an odd root. So when the index is an odd number, such as 3, 5, 7, any odd number that you can think of, you will not have any restrictions on your domain for that function. However, when your root is even, when the index is even, such as here, even though there isn't a 2 there, we know that this symbol means square root. So whenever you have an even index, you will be dealing with restrictions because you cannot have a negative as a radicand. Okay, let's take a look at the third function that we have here. We have f of x is equal to 1/3 the cube root of 4 minus x. Does this 1/3 do anything to our domain? It does not. It only affects the range. So for now, we're not going to be concerned about this value here of 1/3. I am concerned, however, of this 4 minus x. Again, since this is a square root, it's an even root, we need to make sure that we do not have any imaginary numbers. So for that reason, we're going to say 4 minus x has to be greater or equal to 0. Well, in this case, I have 4 minus x. I want a positive x, so I am going to add x to both sides, and that leaves me with 4 is greater or equal to x. Well, what does that mean? It means that x has to be less than or equal to 4. Okay. These two expressions mean the same thing. It's just the order in which we're saying it. But in this first expression, we say 4 greater or equal to x. That means that x has to be less than or equal to 4. So our domain is x less than or equal to 4. Now, here in the examples 4 and 5, we need to determine why the graph is not the graph of each of these equations here. So let's start with number 4. And it's asking us why graph A is not the graph of y equals square root of x minus 1 plus 2. So if you recall, when we were learning about transformations of functions, we said that h comma k was a key point in our graphs. And the h value always appears where there is an x. So in this case, minus 1. X minus 1 is inside of the square root sign. So my h is the 1. And my k is outside of the square root sign. So I have an h value of 1 and a k value of 2. So my starting point must be 1 comma 2. Let's look at the graph here. We're starting at 2 comma 1. We should have started at 1 comma 2. So this graph should be up here, not down here. Okay, let's take a look at number 5. Let's explain why graph B is not the graph of y equals cube root of x plus 2 minus 3. Once again, this positive 2 is attached to my x because it's inside of the cube root sign. And if you recall, we need to have x minus h as our function. So since we have a plus 2, what would have turned the negative sign to a plus? The only way that would have happened is if we have a negative 2 for our x value. So h has to be negative 2, and k is negative 3. Now with a cube root function, the h comma k is not our starting point, but rather the bend. So where your function goes and turns. Okay, see how it looks like a elongated S in a horizontal way? This little point here is the bend, and that should be at negative 2, negative 3. Well, negative 2, negative 3, x is negative 2, and y is negative 3, would have to be right here. So this graph would have to have slide over to the left. Okay, so be careful when you're graphing these functions, because it matters where you start and it matters where the bend is. So let's take a look at some rules when we're graphing. Okay, so here we have the parent functions. So recall from previous types of graphs that our parent function tells us what the graph will look like. And then the transformation tells us whether we're stretching in a vertical or horizontal direction, or if we're compressing horizontally or vertically, or whether we're moving left, right, up, down. But our function will always look in this manner. So the cubic root function will always look like half of a parabola that went sideways. And it makes sense that it looks like part of a parabola because the square root function is the inverse of the parabola y equals x squared. Now the cube root function looks like a stretched S that has been stretched horizontally, not vertically. And that's because it is the inverse of x to the third power. So the domain for our square root of x function is always going to be x is greater or equal to 0, and the range is y is greater or equal to 0. Now, recall that that's the domain and the range for the parent function. Once we start doing transformations, that is going to change. Okay, so in the past, we learned that A is in charge of telling us whether we're stretching or compressing and whether we have a reflection over the x-axis. This H tells us whether we're moving left or right on our function. So whether this function is moving left, then you would have to have a plus H here. And if we're moving right, then we have that minus H. And this plus K is telling us whether we're going to be sliding up or down. So HK tells us the translation, moving left, right, up, down, while A tells us whether we're reflecting over the x-axis or if we're going to be shrinking the function or stretching it out. Okay, same thing with the cube root function. The domain and range for the cube root function is all real numbers. So if we have all real numbers, as you can see, as x goes from left to right, so from negative infinity to positive infinity, we do not have any breaks in the graph. And for that reason, we can have a domain that is all real numbers. And same thing for the range. As you can see, this graph, no matter what the x value is either going to go towards negative infinity in the y direction or positive infinity in the as x goes to positive infinity. Okay, so there isn't much difference in terms of the way the functions look. We have a in both of them. The h is part of the radicand, and the k is outside of the radicand. Okay. Okay, the h comma k is the initial point of the square root function, while the h comma k is the bend of our function. Okay, and let's remember that a is telling us the stretch or compression of the function and whether we reflect over the x-axis. So if we have a negative a, we're going to reflect on the x-axis. And the h and k tell us whether we're shifting left or right for h and shifting up or down for k. Okay, I hope you found this helpful.